In an optical clock, the ticking is 100,000 times faster than in a conventional atomic clock, making them more stable and more accurate.
In the previous video, we saw that atomic clocks are based on the frequency of light that atoms emit. The main building blocks for these clocks are the atoms themselves. But an almost equally important role is played by lasers.
In the iqClock project, we are raising an optical clock where thousands of atoms trapped in an optical lattice are measured by an ultra-stable laser. One of the key technologies in the realization of such clocks are the laser systems. They are used to cool down, trap, or manipulate the atoms before probing them. We, at Toptica Photonics, contribute with our expertise in the realization of such complex systems.
The iqClock project aims to bring extremely accurate atomic clocks to society. At the heart of these clocks is a laser that probes the atoms. Its light is synchronized with the frequency of the atomic transition. The output of such an optical clock is the frequency of the beam of laser light.
In an optical clock, the ticking is 100,000 times faster than in a conventional atomic clock, making them more stable and more accurate. The enabling technology in the realization of such clock are on one side new laser sources. Here, for example, we are working with strontium atoms and they need many blue and red lasers. On the other hand, optical frequency cannot be measured by electronics. Therefore, we are using frequency comp technology in order to transfer the stability of the optical clock down to the radio frequencies. Finally, an all-wavelength approach allows us to build clocks with many different atoms, such as ytterbium, mercury, or aluminium.
Conventional atomic clocks use cesium atoms for their timekeeping. However, cesium emits microwaves with a low frequency. The atoms in modern and more accurate optical clocks, such as strontium and ytterbium, emit visible light with a much higher frequency. In the iqClock project, strontium is the element of choice. Even in optical clocks, the traditional lasers used to probe the atoms can cause problems. The laser light waves are stabilized in a second empty cavity. This cavity can change its length or vibrate, resulting in tiny errors in the timekeeping. A solution is superradiance. Here the light of the laser comes from a gas of strontium atoms in a cavity and directly has the correct frequency. For superradiant lasers, their light is barely influenced by length changes of the cavity.
One very promising technology for new clocks are superradiant lasers, which are currently only realized in research laboratories. As a high-tech company, it is very interesting to work together with our partner on such innovative research, and hopefully in the near future we can bring together superradiant lasers outside of laboratories.
Superradiant lasers possess an additional advantage. Since they already contain atoms emitting light, one can use the strontium atoms for this directly. No more synchronization with other atoms is needed. A clever idea, but getting this to work is not as easy as it sounds. In fact, it is one of the goals of the iqClock endeavor that we'll describe in the 6th and final video of this series. So, keep watching!